Good morning. My name is Josh Converse. I'm the founder of Dynamic Offset, and we're a boutique consulting firm that specializes in mobile and conversational software. So today, through kind of the lens of building distributed systems, we're going to talk about how Rasa and other open source software can really up your product's game. But first, let's talk about the Beatles for a brief moment. So it's been said of the Beatles that the whole is greater than the sum of its parts. Four musicians coming together in a way that far outshines their individual abilities. We're going to come back to this in a little bit, but I just want to prime you to think about your systems like a band, with each part playing off of the others to make something bigger, something better, something larger than the sum of its parts. And to start things off, I'm going to show you a demo. And as part of a startup effort, we set out to build a digital receptionist that could answer the phone for a business and service that call just like a human receptionist would. In short, right, it needed to have a conversation just like you and I would have. And in this demo, we're actually calling a hair salon to schedule an appointment.
Hi, I'm Spoil Me Salon's automated assistant. What can I do for you?
I'd like to schedule an appointment for tomorrow.
What would you like to come in for?
A beard trim.
Can you do tomorrow at 9 a.m.? I have an opening then for a beard trim.
What are your business hours?
We're open 7 days a week from 9 a.m. until 5 p.m.
What about Sunday instead?
I have an opening for a beard trim Sunday at 3:30 p.m. Will that work?
Yeah, that'll work.
Can I get your name, please?
Josh.
Is this number ending in 4111 a good way to reach you?
Yep.
You're confirmed, Josh, for a beard trim Sunday at 3:30 p.m. Is there anything else I can do for you today?
Nope, that's it.
Have a great day.
So that was a real phone call to a real running service scheduling an appointment. Pretty neat. At a conceptual level, what actually goes into building a system like this? Well, there's a few main parts, right? There's VoIP connectivity, there's speech to text, text to speech, as well as an autonomous agent that's driving the show. So let's go through the stages piece by piece. First, the telephony carrier receives a call from the regular copper phone network and starts a VoIP call to our system. That call is answered, and that audio is streamed to a speech-to-text system for transcription. That audio stream is converted to text and forwarded over to the agent for handling. And then the agent will interpret that text relative to the whole conversation, ultimately taking some sort of action. Let's break that into a few steps in and of itself. First, of course, the text is classified into structured data. That data is then evaluated relative to the conversation as a whole. And then the agent decides how to react. None of this should feel surprising, right? This is what Alan just went over. And the agent decides how to react, such as a spoken response, some database access. And then having decided what it should say and do, the agent provides a response. That is then synthesized using a text-to-speech system, fed into the telephony system so that it can go into the ongoing VoIP call. And then finally, our VoIP provider bridges that audio between the VoIP call and the copper phone network. All right, it seems pretty straightforward, but what actually goes into building a system like that? Well, so that demo that you saw actually utilized quite a few technologies, right? On the voice side, we had Twilio, Chimelio, Asterisk. For speech, we were using Google Cloud and Amazon Polly. Persistence was handled by MongoDB. And of course, Rasa made up the core of the whole system. So let's go back through that step by step with the specific technologies. So first, Twilio receives a phone call from the copper network. In this case, it's our customer calling to schedule an appointment. As that regular call comes in, they initiate a VoIP call to our Chimelio server. You can think of Chameleon like a load balancer for VoIP systems. Chameleon then connects that VoIP call to our asterisk server, which does a few things. Right? It answers the call, it starts a conversation with our agent who's going to issue a greeting, and it taps into that audio stream and sends it off for real-time transcription. We used Google Cloud speech-to-text to transcribe in real time and then stream those results straight to our Rasa agent. And then that agent ultimately decides what should happen. Let's go through that process. Right? Rasa NLU classifies the customer's words into structured intents. So for example, the phrase, "My name is Josh," got classified into an informed name intent, while the phrase, "What about Sunday instead?" classifies as a request time slot intent. And then Rasa Core would evaluate those intents in the context of the entire conversation. So in the demo, the phrase, "What about Sunday instead?" came after the question, "What are your business hours?" But because the customer was talking earlier about scheduling an appointment, Rasa Core is able to understand that that request time slot intent is really part of the scheduling flow and not about business hours. And then Rasa Core will emit various actions that need to be performed in response to that conversation. So in this example, it's a query to MongoDB to look up some time slots, followed by a response suggesting a time for the appointment. Okay, so now we've got a response from the agent suggesting a time slot. That gets sent to Amazon Polly text-to-speech for synthesis into an actual voice. Polly would synthesize that audio, and we'd feed it over to Asterisk to be joined with the VoIP call. Asterisk injects that into the VoIP call, and finally Twilio bridges that audio back over to the copper lines where the customer hears the agent's response. And then, of course, this diagram is just one tiny pass through the process. The user and the agent are going to continue conversing back and forth throughout the duration of the phone call. But even that flow is still a bit too high level. Let's actually look at the architecture diagram of the system that ran that demo. It turns out there are a lot of moving pieces. Some of the boxes in that previous diagram were actually multiple processes that were working together. And remember, this is all in real time. In a distributed system like this, there are a lot of systems interacting. In fact, a single instance of this architecture has no fewer than 10 distinct processes that are all coordinating to service a single phone call. And when you start factoring in replication and fault tolerance, there's actually a lot more going on. Turns out that's a lot of software that you have to write. Except you don't have to write it all. As a matter of fact, much of the code that was powering this receptionist was open source software. So what you'll see behind me, I've highlighted the parts that were actually written by me. It's a lot less than it seems, and a non-trivial chunk of that is simply configuration. Which brings me to one of the core points that I want to make, is that right now, we live in a golden age of open source software. There are open source libraries, editors, paradigms, platforms, frameworks, manifestos. There is a lot of fantastic software out there that you simply don't have to write. Let's come back to the Beatles. If we were to think of our product maybe like a band, then perhaps open source software would be like guitarist George Harrison, right? Providing a set of riffs and licks that can be woven together to form a beautiful melody. Don't worry, you're gonna get sick of this metaphor by the time I'm done. Okay, so we've gone out and we've gathered a bunch of open source software that we want to glue together to build our amazing product. With so many packages all talking to one another, system management really becomes an issue. And so that's why I wanted to take a moment to talk about one of my favorite open source projects, which is Kubernetes. And what is Kubernetes? In short, it lets you manage a fleet of machines. So whether you're running in your own data center, a public cloud, a private cloud, it can handle the resources, the networking, the overall environment, and distribute work across that fleet of machines. This, in turn, frees you up to start architecting your system as a whole, rather than working on allocating individual resources, choosing what process runs on which machine. But what does that actually mean? Right, so on the left side of this diagram, I've specified some requirements about the software that needs to run on our system. 2 instances of Elasticsearch, 3 of Nginx, and a pair of Rasa agents that should only run on machines that have GPUs. On the right, we've got our 4-node Kubernetes cluster, with half of the machines having GPUs in them. The Kubernetes control plane takes our requirements, which are specified via an API, and then schedules them for execution across the fleet of machines, and takes care of making sure that they can talk to one another, sets up all of the networking, all of the routing, does it all for you. But now let's imagine that something went wrong and one of our Nginx instances died. Well, Kubernetes will see that the state of the world doesn't match the way we want it. Namely, there's supposed to be 3 instances of Nginx running. So it'll start up another instance, maybe running on a completely different machine, in order to get the world back into a correct state. So why is this pertinent? Well, whether it's due to scale, complexity, the way your system utilizes machines, monolithic systems often struggle. And meanwhile, trying to hand manage a cluster and cobble together a solution, it's time-consuming and error-prone. You've got better things to do. I want to encourage you to think about your products as a system, as a set of disparate pieces that are talking together to perform the actions that you want to take. Farm out that mundane work to Kubernetes, and instead focus on what makes your product great. All this is to say, Kubernetes can manage your fleet so that you don't have to. And as a matter of fact, I like to think of Kubernetes kind of like the drummer Ringo Starr, right? Laying down this solid rhythmic foundation on which a great song can be built. All right, so thus far, this has been a wonderfully adequate distributed systems presentation, but we are at the Rasa Developer Summit. So let's talk a little bit about Rasa. And because this is very much a high-level systems talk, I want to prime you to think about how Rasa can add flexibility into your systems. And this is the theme that I want you to take away. And that flexibility ultimately comes from the fact that at the heart of it all, Rasa Core is a dialogue engine. Instead of writing imperative logic, wiring flows together by hand, you provide Rasa with training samples, and it creates a machine learning model. And using that model, Rasa Core can then respond to your users and affect change within your system. And I'm going to breeze through this because this is the same as what Alan described. These example conversations, they just represent a known good encounter that the agents should try and mimic. And there are a few different things that go into this training data. User stimuli, responses to that stimuli, and contexts, such as what happened earlier in the conversation. And one of the cool things is that with a robust enough set of training data, the agent is going to learn what actions it should take based on stimuli, including things that it's never seen before. And this is where some of that flexibility really comes into play, reacting to these unseen situations. As a short aside, well, what is an action? Well, as Alan pointed out, you can write arbitrary code. And while useful, an agent that responds with just canned responses, it's not very interesting. And the way we, as developers, make them more useful are by writing these actions. The important part here is that they're the bridge between your agent and the rest of your system. As a matter of fact, let's look at a snippet of a training sample with a few actions. Here, the user asked for the menu of a restaurant. The agent performed a search and needed a bit of disambiguation. So it asked the user, who provided a location. From there, the agent performed some more lookups and sent the menu. The actions on the right-hand side here, such as searching the DB for a restaurant or looking up a menu for a restaurant, sending messages over SMS, or sending a copy of the menu. These are all contrived actions, but imagine for your domain, for your space, there's a lot more complex things that you can do. And the point I really want to drive home here, and this is something that really blew my mind as I was getting into this, is that you can drive the behavior of your entire system using Rasa. If you've got an expressive enough set of actions, an expressive vocabulary of things that your agent can do, when you couple that with a distributed system that is servicing these actions, the sky's the limit. This wasn't really obvious to me at first, that Rasa can be the brain driving your entire system. But once it clicked, I found it really magical. The point being, Rasa can introduce a huge degree of flexibility into your system. Instead of you hard coding these flows and behaviors, implement actions, run them on your cluster, and train Rasa to use them on your user's behalf. As you listen to the suite of talks and panels today, I want to encourage you to really reflect on that flexibility aspect and how you can offload more and more work to Rasa to make your systems really shine. I kind of like to think of Rasa like singer and songwriter Paul McCartney, bringing a voice to your product, really just controlling the flow of your entire song. And then finally, there's you. You're the John Lennon of this band. You bring all of the pieces together. You're the one making something amazing, something that is greater than the sum of its parts. As you go through the day today, I encourage you to think about how you can leverage a systems-based approach and control it but with Rasa, with that flexibility that it brings. And with that, I want to thank you for your time and take any questions that you may have. That's a fantastic question. We've been kind of, so for the record, the question was, how do you handle a slow part of the system not tanking your experience elsewhere within your system? We've been trained for the longest time that latency is really bad, right? When you are loading a web page almost instantaneously or making your app feel responsive. We have this interesting situation in conversations where if your agent responds too quickly, especially in spoken situations, it falls into that kind of uncanny valley of, oh, this is kind of creepy. So I would actually argue that the latency constraints of a conversational system, especially one with a voice, are much less tight than a traditional system. And as a matter of fact, latency can be good. And there's even been some research of introducing and little pauses in agent responses to make it sound more human. So I would argue that you need to be quick, but you don't need to be lightning quick. Go ahead. So in the system that I built for this, let me pull up. In this situation, because we had a lot of pieces going on simultaneously, we would have, for example, one agent servicing multiple conversations at a time. It really depends on the workloads. And so, for example, your Rasa bot may, because it is running this potentially complex machine learning model, might need a bit more resources. So you might need to expand that out to have maybe 5 or 10 instances, whereas the call bridge, which is just the bit that's answering phone calls, kind of connecting pieces together, may only need 1 or 2 instances to service the workload. I think that's the really interesting thing about a system like Kubernetes. Suddenly, when you're debugging your systems or you're looking at your metrics, things are slowing down in this one spot. Well, I'll just ramp up the number of processes, and suddenly it just works. Because you've already built in this distributed fashion, you just crank up the number, and suddenly you are now dealing with this capacity.